Hello there, and welcome to Sleepy Science Vault. The universe, when you look closely enough, is not really made of single objects at all. It's made of arrangements. Patterns within patterns, galaxies gathered into groups, groups gathered into clusters, clusters strung together into filaments that stretch across almost unimaginable distances. And in between all of that, vast, quiet voids, where almost nothing exists at all. Tonight, we're going to drift through those arrangements slowly, one layer at a time, starting small and drifting outward, further and further, until the scale becomes almost too large to hold in the mind. Let's begin gently. NASA describes galaxy groups and clusters as the basic building blocks of the largest structures in the universe. Not the finished structures themselves, but the foundation everything else is built from. Small communities of galaxies, drawn together by gravity, forming the first true gathering point above a single galaxy on its own. A galaxy group, in most cases, contains around 100 galaxies or fewer. That might sound like a lot, but compared to what comes later, it's actually quite modest. Groups are cozy, in cosmic terms. Close-knit. A neighborhood, rather than a city. And we happen to live inside one. The Milky Way belongs to what astronomers simply call the local group. It's home to more than 50 known galaxies, drifting together through space, bound loosely by gravity across millions of light years. Our closest large neighbor within this group is Andromeda, a galaxy so massive that one day, in the far distant future, it will merge with our own. But that's a story for another night. For now, just picture it. 50 or more galaxies, moving slowly together through the dark, part of the same gravitational family. Our galaxy is not alone out there, it has company. Quiet, distant, patient company. From here, the scale begins to grow. Beyond galaxy groups, we find galaxy clusters, structures far larger, far denser, containing far more galaxies bound together by gravity. One of the most well-known examples is the Coma cluster. The Coma cluster contains more than 1,000 galaxies. Not 50, not 100, over 1,000. All gravitationally bound within a region more than 20 million light-years across. Try, for a moment, to imagine that distance. Light, the fastest thing in existence, would need 20 million years just to cross from one side of this cluster to the other. And within that immense span, galaxy after galaxy after galaxy, drifting together in a slow cosmic dance that has been unfolding for billions of years. Not far from Coma, at least on a cosmic map, lies another giant, the Perseus cluster. Perseus is considered one of the largest known galaxy clusters in the observable universe. It holds thousands of galaxies, all suspended within an enormous, glowing envelope of superheated gas. This gas isn't something you'd notice by eye, it's mostly visible in X-ray light, but it plays an important role. It fills the space between galaxies, tracing out the cluster's true size and mass, revealing structure that would otherwise stay hidden in visible light alone. Picture it like this. Galaxies as bright, scattered lights, and around them, threading everything together, an invisible sea of scorching gas, holding the whole system in place. It's easy to think a structure like Perseus, thousands of galaxies bound in hot gas, must be about as large as things get. But it isn't. Above galaxy clusters, there's another level entirely: galaxy superclusters. These are enormous collections of clusters and groups, gathered loosely across hundreds of millions of light years. Our own Milky Way belongs to one of these, a supercluster known as Laniakea. Laniakea is a Hawaiian word meaning immense heaven, and it's a fitting name. Laniakea contains our local group, the Virgo cluster, and thousands of other galaxies, all part of the same immense flow through space. But here's something important, something that separates superclusters from the smaller structures we mentioned earlier. Superclusters are not gravitationally bound the way clusters and groups are. Their galaxies are not locked together forever, orbiting one shared center. Instead, they're more like a loose current, a general drift in the same direction, shaped by gravity across a much larger scale, but without the tight, permanent grip that holds a cluster like Coma or Perseus together. Over the long, slow arc of cosmic time, this means superclusters will eventually stretch apart, their galaxies drifting further and further from one another, carried outward by the ongoing expansion of the universe itself. It's a strange kind of structure, when you think about it. Real, measurable, vast, and yet, ultimately, temporary. One of the most massive superclusters near our own region of the universe is the Shapley supercluster. It's often used by astronomers as a kind of reference point, a landmark for measuring and comparing other nearby large-scale structures. Shapley is so massive that its gravity subtly influences the motion of galaxies across a huge surrounding region, including, in a very small way, our own. Even from hundreds of millions of light years away, its presence can still be felt. And then, beyond even superclusters, astronomers eventually discovered something stranger still: structures made not just of clusters, but of superclusters themselves, linked together into even larger complexes. One of the first such structures ever identified was the Pisces-Cetus supercluster complex. It was, in many ways, a turning point. Before its discovery, superclusters like Shapley or Laniakea were often thought of as close to the upper limit of cosmic structure, vast, but with a ceiling. Pisces-Cetus suggested something different. It hinted that superclusters themselves could align, stretch, and connect into structures far beyond what anyone had expected, shapes so large they blurred the very definition of what a single structure even means. And that is where we'll pause for now. Groups, clusters, superclusters, and now, hints of something even larger still forming on the horizon of our understanding. Rest here for a moment, if you'd like. Let these first layers settle quietly in your mind, before we drift further outward, into structures larger still. Let's continue exploring, this time from a direction much closer home. Our own galaxy sits within something astronomers call the Virgo supercluster, a broad gathering of galaxy clusters and groups that includes the Milky Way itself. According to several large-scale maps of the universe, the Virgo supercluster isn't an isolated formation. It appears to be part of something even larger, a long strand of structure known as the Pisces-Cetus filament, the very complex we touched on a moment ago. It's a curious thought. The supercluster we belong to, the one containing our own galaxy, may simply be one segment of a much longer structure stretching far beyond anything we could hope to see with the naked eye. In 2017, astronomers identified another massive structure in the direction of the constellation Pisces. At the time, it was described as one of the largest nearby structures ever mapped, a sprawling supercluster whose true scale surprised many researchers studying it. Discoveries like this remind us how much is still being uncovered, even in our own cosmic backyard, relatively speaking. Space, it seems, always has more to reveal. To understand structures like these, and the ones still to come, it helps to step back and look at the bigger picture, quite literally. Because underlying everything we've discussed so far, from galaxy groups to sprawling superclusters, is something astronomers call the cosmic web. The cosmic web is the largest known pattern in the universe. It formed billions of years ago, shortly after the Big Bang, when matter, not evenly spread, but slightly clumped in places, began collapsing under the pull of gravity. Regions with a little more mass pulled in more material. Regions with less became emptier still. Over vast stretches of time, this process carved the universe into a pattern that still exists today. That pattern has four basic ingredients: clusters, filaments, walls, and voids. Clusters are the dense nodes, the places where galaxies gather most tightly, much like the ones we described earlier. Filaments are the thread-like strands connecting those clusters together, acting almost like bridges, or perhaps more fittingly, like connective tissue linking one dense region to the next. Walls are broader, flatter formations, which we'll return to shortly. And voids are the vast, mostly empty spaces in between, regions where galaxies are remarkably scarce. Together, these four elements form a structure that some scientists compare to scaffolding, an underlying framework upon which galaxies have been arranged, thread by thread, node by node, across billions of light years. Galaxies aren't scattered randomly through space. They follow this hidden architecture, clustering along filaments, gathering at intersections, and thinning out dramatically wherever a void begins. Other researchers describe the cosmic web using a different image altogether: foam. Picture the bubbles in sea foam, thin walls of material surrounding large empty pockets of air. The cosmic web has a similar quality. Dense strands and nodes form the walls of the foam, while the void regions sit inside, like the empty air pockets between bubbles. It's a strange, almost delicate way to imagine the universe: vast cosmic foam, spun out across unimaginable distances, with entire galaxies caught along its edges like droplets of water clinging to a bubble's surface. Let's slow down and look more closely at the filaments themselves, since they play such an important role in the wider structure. A filament is, in essence, a long, thin bridge of galaxies. Its length is usually far greater than its width, sometimes dramatically so. Some filaments stretch across hundreds of millions of light years, while remaining comparatively narrow along their width. If you could view one from a great enough distance, it might resemble a glowing thread, stretched taut across the darkness, connecting two much larger, denser regions on either end. These filaments are where much of the connective work of the universe happens. Galaxies migrate slowly along them, pulled gently by gravity toward the denser clusters at either end. Matter doesn't simply appear scattered evenly through space, it flows, almost like water trickling down towards a low point, following invisible channels laid out by gravity billions of years ago. Now, walls are a little different. While filaments are narrow and thread-like, walls are broader, flatter, closer to enormous sheets of galaxies than narrow strands. Imagine, if you will, an enormous curtain of galaxies stretched out across space, wide and expansive, yet remarkably thin when compared to its overall size. That's the basic shape of a cosmic wall. Because both walls and superclusters can be extremely large, astronomers often need another way to tell them apart. And usually, that distinction comes down to shape. Superclusters tend to be more irregular, clumped loosely around multiple dense regions. Walls, on the other hand, tend to be flatter and more elongated, more like a sheet stretched in two directions, rather than a cluster bulging outward in several. It's a subtle but important difference, and one that becomes clearer the more these structures are mapped and studied. To really appreciate just how thin these walls can be, relative to their size, it helps to imagine scale in a very deliberate way. Some cosmic walls stretch for hundreds of millions of light years in length, and yet remain remarkably thin when measured across their depth. If you could shrink a structure like this down to fit on a table in front of you, it might resemble a single sheet of paper, laid out flat, impossibly wide compared to how thin it truly is. That's part of why astronomers often use the word sheet to describe them. Wide, layered, expansive, and yet, in cosmic terms, astonishingly delicate. When you place all of this together, the clusters, the filaments, the walls, the voids, a picture starts to form. Not of a universe filled uniformly with galaxies, scattered evenly like grains of sand, but of a universe shaped, structured, almost woven, into an enormous, breathing lattice, stretching in every direction as far as our instruments can currently see. And we are here, inside it. Part of the weave itself. Our galaxy resting somewhere along one gentle strand of this vast, foam-like universe, connected, quietly, to structures whose true scale we're only beginning to understand. For now, let this settle. Filaments, walls, voids, clusters, each one a piece of the same enormous puzzle. Let your mind rest quietly here for a moment, drifting gently along one of these invisible threads, before we continue outward, deeper into the cosmic web, in the segment to come. Let's continue further outward, towards some of the largest structures ever mapped by human hands. Among all the walls we touched on briefly before, two stand out in particular, not just for their size, but for what their discovery meant to astronomers trying to understand the true scale of the universe. The Quipu Wall and the Sloan Great Wall. The Quipu Wall stretches for hundreds of millions of light years, threading its way through space, dense with galaxies gathered along its length. And the Sloan Great Wall, discovered through one of the largest galaxy surveys ever conducted, reaches even further still, over 1 billion light years from end to end. To put that into perspective, light itself, moving at the fastest speed anything can travel, would need more than 1 billion years just to cross from one side of this structure to the other. 1 billion years. Long before humans existed. long before the Earth even looked the way it does now. That's how long it would take light to simply span the length of the Sloan Great Wall. NASA has described walls and sheets like these as likely being the largest known superstructures in the observable universe. Not the only large structures, certainly, but among the very largest ever confirmed. Vast curtains of galaxies, stretched taut across unimaginable distances, forming some of the outermost edges of what we currently understand about cosmic structure. It's worth pausing here, just for a moment, to really sit with that idea. We began this journey with galaxy groups, modest gatherings of a few dozen galaxies. And now, only a short while later, we find ourselves facing structures over 1 billion light-years long. The scale has grown so far beyond ordinary comprehension that words like large almost start to lose their meaning. And yet, for every towering wall of galaxies, for every dense, glowing filament, there exists its opposite. A quiet counterbalance. Cosmic voids. Voids are the great empty regions of the universe, vast stretches of space where galaxies are remarkably scarce, sometimes almost entirely absent. One of the most well-known examples is the Borealis Void, sometimes nicknamed, half-jokingly, the Great Nothing. It spans hundreds of millions of light-years, and within that colossal space, there is startlingly little. A handful of galaxies, scattered thin and lonely, surrounded by an emptiness so vast it's difficult to picture. Imagine standing at the very center of a void like this, if such a thing were even possible. Looking outward in every direction, and seeing almost nothing. No familiar clusters. No walls of light stretching across the sky. Just darkness, extending for hundreds of millions of light-years, before finally reaching the edge of some distant structure far, far away. It's a strange kind of stillness. Peaceful, in its own quiet way, and yet almost unsettling, once you truly consider the scale of it. But even within these voids, and within the vast stretches of space that lie between galaxies everywhere, the universe is never truly, completely empty. Between galaxies lies something astronomers call the intergalactic medium, an extremely thin scattering of gas and plasma, spread out across space. It's incredibly difficult to detect directly. Unlike the bright, glowing material found inside galaxies, this intergalactic material is so sparse, so faint, that it often goes almost unnoticed, even though it fills an enormous portion of the universe's overall volume. Much of it is made up of hydrogen and helium, the two lightest, simplest elements, left over from the earliest moments of the universe, shortly after the Big Bang itself. In many ways, this thin intergalactic gas is some of the oldest material in existence, drifting quietly through space for billions of years, largely undisturbed, tracing a story that stretches back to the very beginning of time. Here's something that might seem contradictory at first. Despite being so faint, so difficult to observe, the intergalactic medium is also, in many regions, incredibly hot. Temperatures can reach millions of degrees. And yet, because the material is spread so thin, so diffuse across such enormous distances, it remains far dimmer, far harder to detect, than the comparatively dense, glowing material found inside galaxies themselves. It's a delicate paradox, when you think about it. Blisteringly hot, and yet almost invisible. energetic, and yet silent, at least to our usual ways of observing the universe. For a long time, astronomers assumed this intergalactic material was made almost entirely of hydrogen and helium, the simplest elements from the universe's early history. But further study revealed something more complex. The intergalactic medium also contains heavier elements: oxygen, neon, magnesium, silicon, sulfur. Elements that didn't exist in the earliest universe at all. So where did they come from? The answer lies inside stars. Over billions of years, generations of stars have lived and died, scattering material outward into space through stellar winds and dramatic events like supernova explosions. Each time a star reaches the end of its life in such a way, it enriches the surrounding space with heavier elements, material that didn't exist when the universe was young, but was instead forged deep within the star's own core. Over time, this enriched material has drifted outward, mixing gradually into the vast intergalactic medium that fills the space between galaxies. In a very real sense, some of the atoms drifting quietly through the space between galaxies right now were once part of a star. Perhaps many stars, across many different corners of the universe. It's a beautiful thought, in its own way. The universe is not static. Matter moves. It transforms. It travels outward from the hearts of dying stars, and eventually settles into the vast, quiet stretches between galaxies, becoming part of something even larger than the star it once belonged to. More recently, scientists have made real progress in tracing this hidden material more directly. New observations have revealed hot gas filaments, threads of extremely faint, superheated material, connecting galaxies and clusters together across space. These filaments are helping researchers locate what's sometimes called the universe's missing baryonic matter, ordinary matter that theoretical models predicted should exist, but which had, for a long time, remained frustratingly difficult to detect directly. Slowly, filament by filament, that missing material is being found, woven quietly into the same vast cosmic web we explored earlier, hidden along threads of hot, thin gas stretched across unimaginable distances. And finally, let's turn to one of the most quietly profound discoveries in the story of large-scale cosmic structure, the Hubble Ultra Deep Field. In the early 2000s, the Hubble Space Telescope was pointed toward a single, extremely small patch of sky, region so small, so seemingly empty, that from Earth it would have appeared to contain almost nothing at all. And yet, over the course of many long exposures, Hubble gathered light from that tiny patch for hundreds of hours, slowly, patiently, allowing incredibly faint, distant light to build up over time. What emerged from that small, dark patch of sky was staggering. Thousands of galaxies. Some among the oldest, faintest, most distant galaxies ever observed, their light having traveled for billions of years before finally reaching our telescopes. But beyond simply revealing the sheer number of galaxies out there, the Hubble Ultra Deep Field also helped confirm something deeply important about how those galaxies are arranged. They weren't scattered randomly across space, the way scattered dust might settle across a table. Instead, they appeared clustered, gathered along particular regions, following patterns, aligned subtly along the same kind of cosmic architecture we've been exploring throughout this entire journey. Groups, clusters, filaments, walls, voids. Even in one of the smallest, faintest patches of sky ever studied in such detail, the same underlying structure appeared. The same thread-like, foam-like pattern, echoing outward across billions of light years, connecting nearly everything we've discussed tonight into one single, unified structure. It's a quiet, remarkable thought to rest on. From the vast, glowing sheets of the Sloan Great Wall, to the almost total emptiness of the Borealis void, to faint filaments of ancient hydrogen drifting silently between galaxies, to distant light captured in a single, tiny patch of sky. All of it, connected. All of it, part of the same extraordinary architecture the universe has been quietly building for billions of years. Let yourself rest here for a while. Walls stretching further than the mind can truly hold. Voids opening into vast, silent emptiness. Faint threads of ancient gas drifting slowly through the dark, carrying with them the echoes of long-vanished stars. And somewhere, quietly nestled among it all, our own small galaxy, and our own small world, drifting gently along one gentle strand of this endless cosmic web. Rest now, for a while, in that vastness, before we continue drifting outward, into the segment still to come. Let's turn now to the tools astronomers actually use to find structures like these, because discovering something a billion light years long is no small task. It requires patience, precision, and a very particular way of looking at the sky. One of the most important techniques is something called a redshift survey. Here's the basic idea, explained gently. As light travels through an expanding universe, it stretches. Its wavelength shifts slightly toward the red end of the spectrum. The further away a galaxy is, generally speaking, the more its light has stretched during its long journey to reach us. By carefully measuring that shift, for galaxy after galaxy, astronomers can estimate how far away each one truly is. And once you know the distance to enough galaxies, not just their position across the flat surface of the sky, but their depth as well, something remarkable happens. A two-dimensional map of scattered points of light becomes a three-dimensional map instead. Suddenly, astronomers aren't just looking at galaxies. They're looking at where those galaxies exist within the actual volume of space. This is how most of the enormous structures we've discussed tonight were originally found. Not through a single telescope image, capturing everything in one glance, but through years, sometimes decades, of painstaking measurement, galaxy by galaxy, redshift by redshift, slowly assembling an enormous three-dimensional map of the universe around us. And once that map begins to take shape, something becomes immediately clear. Galaxies are not scattered evenly throughout space. They cluster. They align. They gather along certain regions, while leaving others almost entirely empty. The same pattern, again and again. Dense knots, long, thin strands, and vast, quiet voids stretched between them. The cosmic web, revealed not through imagination, but through careful, patient measurement. It's worth remembering, too, that what these surveys reveal isn't limited to galaxies alone. Some of the largest confirmed structures in the universe include enormous filaments made not just of visible galaxies, but of dark matter and gas as well, material that doesn't glow, doesn't shine, and can't be seen directly through any telescope. Its presence is inferred instead, through the way it gently bends light, or through the gravitational influence it has on the galaxies scattered along its length. In many ways, the galaxies we do see, the bright, glowing points that first reveal a filament or a wall, are really just a kind of tracer. A faint outline, sketched in visible light, hinting at a much larger, much heavier structure lying mostly unseen underneath. Now, when astronomers describe just how large these structures truly are, they usually don't reach for total mass, or overall volume, the way you might expect. Instead, they often describe a structure by its longest dimension, how far it stretches, from one end to the other, along its greatest length. This is partly practical. Mass can be difficult to measure precisely, especially for structures containing large amounts of unseen dark matter. But length can be measured more directly, especially once redshift surveys reveal how far a structure spans across three-dimensional space. So when you hear a wall or a filament described as being some enormous number of light-years long, that measurement usually refers to this longest stretch, the greatest distance from one edge of the structure to the other. And to measure distances on scales this large, astronomers typically turn to a unit you may not use very often in everyday life, the megaparsec. A megaparsec is roughly 3.26 million light-years. It's a unit built specifically for scales far beyond anything human experience naturally prepares us for. Even a single megaparsec is difficult to picture in ordinary terms. And yet, when describing the very largest structures in the universe, astronomers often need hundreds of megaparsecs just to capture their full length. It's a strange kind of vocabulary, when you think about it, a unit invented simply because the universe, in its largest form, refuses to fit inside the numbers we're used to. Let's return, for a moment, to a structure we touched on briefly earlier, the Coma Wall. The Coma Wall holds a special place in the story of large-scale cosmic structure, because it was the very first galaxy wall astronomers ever identified. It was discovered back in 1989, during one of the earliest large-scale redshift surveys ever conducted. At the time, nothing quite like it had ever been confirmed before. A vast, elongated sheet of galaxies, stretching across space in a way that hinted at something far larger than the individual clusters astronomers had studied up until that point. Its discovery marked a quiet turning point in cosmology. For the first time, there was solid evidence that structure in the universe extended far beyond individual clusters and superclusters, that galaxies could align into vast, sheet-like formations, stretching across hundreds of millions of light-years. The Coma Wall lies roughly 300 million light-years from Earth, reasonably close, at least in cosmic terms, when compared with some of the more distant structures discovered since. And its size, once properly measured, turned out to be extraordinary. The Coma Wall stretches for about 185 megaparsecs, which translates to roughly 600 million light-years from end to end. 600 million light-years. Let that settle for a moment. Light, moving at the fastest possible speed in the universe, would need 600 million years just to travel the length of this single structure. For comparison, complex life had barely begun appearing on Earth 600 million years ago. And that entire span of time, that entire, almost incomprehensible stretch of years, is roughly how long it would take a beam of light to simply cross from one end of the coma wall to the other. And this was only the beginning. Once astronomers realized structures like the coma wall existed, and once they had developed reliable methods, through redshift surveys, and careful three-dimensional mapping, to detect them, an entirely new chapter in cosmology began. Larger surveys followed. Larger maps were built. And with each new survey, astronomers began uncovering structures even larger still, walls and filaments stretching not hundreds, but eventually well over 1 billion light-years across, some of which we've already touched on, and others still waiting for us, further along in this journey. It's a remarkable thing, when you consider it quietly. A structure like the coma wall wasn't simply sitting there, waiting to be casually noticed. It had to be uncovered, patiently, through years of careful measurement, one galaxy, one redshift, one tiny data point at a time, slowly assembling into a picture too large for any single glance to capture. And that, perhaps, is one of the most beautiful parts of this entire story. The universe's largest structures were never obvious. They were never simply visible, waiting in plain sight. They had to be found, slowly, patiently, piece by piece, by people looking upward and outward, with extraordinary care. For now, let this rest quietly in your mind. Redshift, distance, megaparsecs, the quiet discovery of the coma wall, back in 1989, when astronomers first realized just how far a single structure could truly stretch. Let yourself settle here for a while, resting somewhere within that 600 million light-year span, before we continue on, drifting further outward, into the segment still to come. Let's spend a little more time with the coma wall before moving further outward, because there's something about its shape, in particular, that deserves a closer look. Earlier, we described the coma wall as stretching roughly 600 million light-years across. Later measurements refined that figure slightly, placing its length closer to 500 million light-years, still an almost incomprehensible distance, even if slightly smaller than first estimated. Numbers like these tend to shift a little as instruments improve, and as astronomers gather more precise data. But the overall picture remains the same. A structure of staggering length, stretched out across the depths of space. What's truly remarkable about the coma wall, though, isn't just its length. It's how astonishingly thin the structure is, relative to how far it stretches. The coma wall is only about 5 megaparsecs thick, which translates to roughly 15 million light-years. And in terms of depth, measured in the third dimension, it comes out to somewhere around 16 million light-years as well. Pause on that comparison for a moment. 500 million light-years long, and yet only about 15 or 16 million light-years thick. If you tried to picture that ratio using something more familiar, it would be a little like comparing the length of a highway to the width of a single lane. The wall stretches on, and on, and on, far longer than it is wide, or deep, in either direction. This is part of what makes the coma wall such a valuable example for astronomers. It beautifully illustrates just how flat, how sheet-like, these enormous cosmic structures can truly be. They aren't spread out evenly in every direction, like a great cosmic cloud. They're thin, elongated, almost like enormous curtains, hung out across the darkness of space, remarkably delicate given their extraordinary length. It's an image worth holding onto quietly for a moment. Somewhere out there, 500 million light-years of galaxies, arranged along a structure barely more than 15 million light-years thick, vast in one direction, and comparatively narrow in the others. A shape that seems almost impossible, and yet, there it is, patiently mapped out across the sky. From here, let's drift toward a structure that, for many years, held the title of the largest confirmed structure ever discovered, the Sloan Great Wall. We touched briefly on the Sloan Great Wall earlier, but it's worth returning to now with a little more care, because its discovery marked such an important moment in the study of cosmic structure. The Sloan Great Wall stretches for approximately 1.37 billion light-years along its longest dimension, 1.37 billion light-years. For a long time, that number represented something close to the outer edge of what astronomers believed cosmic structure could even look like. A single, connected arrangement of galaxies, so vast that light itself would need well over 1 billion years just to travel from one end to the other. Since its discovery, the Sloan Great Wall has remained something of a benchmark, a familiar reference point that astronomers still return to, even now, whenever a newly discovered structure is being measured and compared. When a new candidate for largest known structure is announced, one of the first questions researchers often ask is simple. How does it compare to the Sloan Great Wall? It's become, in a sense, a kind of quiet measuring stick for the universe itself. And much like the Como Wall before it, the Sloan Great Wall shares that same striking characteristic, enormous length, paired with surprising thinness. Many of these great walls, astronomers have found, tend to be only about 10 to 20 million light-years deep, even while stretching across hundreds of millions, or in some cases, well over 1 billion light-years in length. It seems to be less of an exception, and more of a pattern. The largest structures in the universe, again and again, take on this same delicate, sheet-like form. Long flat, stretched impossibly thin, given their overall scale. Perhaps this shouldn't be too surprising, once you consider how these structures actually formed. Matter didn't collapse randomly, in every direction, at every point in space. It followed the underlying pull of gravity, flowing along particular paths, converging where the pull was strongest, and thinning out elsewhere. Walls may simply be a natural outcome of that process, regions where matter gathered along a broad, flattened front, rather than compressing evenly into a single, rounded shape. Whatever the deeper explanation, the result is the same. Some of the largest, most massive structures ever confirmed in the universe are also, in their own way, remarkably delicate. Vast sheets of galaxies, spread thin across the darkness, like something almost fragile, despite their staggering size. Now, let's move to a structure discovered far more recently, one that reminds us this story is still very much unfolding, even today. In 2020, astronomers announced the discovery of an enormous structure known as the South Pole Wall. And despite being identified so much more recently than the Sloan Great Wall, it appears to rival that earlier structure in overall scale, one of the largest formations ever confirmed, sitting quietly, largely unnoticed, for who knows how long, before finally being mapped in detail. Part of the reason the South Pole Wall remained hidden for so long comes down to its location. Much of the structure lies in a region of the sky that's difficult to observe from many major observatories, particularly those in the northern hemisphere. It required more specialized surveys, focused specifically on the southern sky, before its true shape and scale could finally be revealed. And what a shape it turned out to be. The South Pole Wall doesn't sit neatly within a small, contained region of the sky. It wraps through an enormous arc, spanning more than 200 degrees. To put that into perspective, a complete circle, from one side of the sky all the way around to the other, spans 360 degrees in total. The South Pole Wall stretches across more than half of that, curving through the darkness in an enormous, sweeping arc, rather than sitting as a simple, compact shape. It's a difficult structure to hold in the mind all at once, precisely because of that curve. We tend to imagine cosmic structures as long, straight formations, stretching from one point directly to another. But the South Pole Wall bends. It sweeps. It follows a great, gentle arc across a huge portion of the observable sky, hinting at just how complex, how organic, these enormous formations can really be. The densest part of this vast structure lies roughly 500 million light-years from Earth, a region where the concentration of galaxies reaches its peak, before thinning outward along the rest of the wall's enormous arc. It's worth sitting with that distance for a moment. 500 million light-years. Roughly comparable to the length of the entire Como Wall, and yet, here, it marks only the densest point of a single structure, a structure that continues stretching, curving, extending outward across the sky, far beyond that central region alone. There's something quietly humbling about a discovery like the South Pole Wall. It wasn't found centuries ago, buried deep in the earliest days of astronomy. It was identified in 2020. Within recent memory, using instruments and survey techniques refined over decades of steady progress. And its discovery serves as a gentle reminder that our current picture of the universe, as detailed and remarkable as it already is, remains incomplete. There are likely still structures out there, every bit as vast as the ones we've explored tonight, quietly waiting in unexplored regions of the sky, simply because no one has yet built the right survey, pointed in the right direction, to reveal them. Let's take a slow, quiet moment here, before continuing further. The Como Wall, 500 million light-years long, yet only 15 million light-years thick, a delicate curtain of galaxies, stretched impossibly thin across the dark. The Sloan Great Wall, over 1 billion light-years across, standing for years as one of the largest confirmed structures ever measured. And now, the South Pole Wall, discovered only recently, curving gently through more than half the sky, its densest heart resting some 500 million light-years away. Each of these structures took shape over billions of years, galaxies, and clusters, and filaments, slowly gathering along paths laid out by gravity, long before life existed anywhere, long before there was anyone to look up and wonder at any of it. And yet here we are now, quietly looking upward, quietly listening, letting these vast, distant shapes settle gently into the mind, one enormous structure at a time. Rest here for a while, if you'd like. There's no need to hold on to every number, every distance, every name. Simply let the shapes themselves settle, long, flat walls of galaxies, curving gently through the darkness, stretching further than imagination comfortably allows, quietly existing, out there, in the vast, patient dark, long before we ever learn to notice them. When you're ready, we'll continue drifting outward, into the segment still to come. Let's return, for a moment, to the South Pole Wall, before we move on to something newer still, because there's one more detail about its shape worth sitting with quietly. We mentioned that this enormous structure curves through more than 200 degrees of sky, sweeping outward in a broad, gentle arc. But part of that arc bends inward as well, closer to us than you might expect. At its nearest point, the South Pole Wall comes to within about 300 million light-years of the Milky Way. 300 million light-years might sound distant, and in many ways, it is. But compared to structures stretching well over 1 billion light-years across, it's remarkably close. Close enough that some astronomers believe this vast wall may be gently influencing the motion of our own galaxy, tugging on us in some small way, alongside other massive structures nearby. We are not simply observers of the South Pole Wall, sitting at a safe distance, watching from somewhere far outside its influence. In some quiet sense, we may be caught within its gravitational reach, one small galaxy, drawn ever so slightly toward the edge of something almost too large to comprehend. It's a strange thought to rest with. A structure spanning more than half the visible sky, invisible to the naked eye, and yet still reaching quietly toward us, across hundreds of millions of light-years of empty space. Now, let's turn to a discovery so recent that many people, even those who follow astronomy closely, may not have heard of it yet. A structure named Quipu. Quipu was first reported in 2025. Which means, as we sit here now, this discovery is still remarkably fresh. Astronomers are only just beginning to understand its full shape, its true scale, and what it might mean for our broader picture of the universe. At its core, Quipu is a major cosmic superstructure, built from an enormous network of galaxy clusters, woven together by vast quantities of dark matter. Like many of the structures we've explored tonight, it isn't a single, solid object. It's a connected system, clusters linked by filaments branching outward in different directions, forming something far larger and far more intricate than any single cluster on its own. What makes Quipu especially interesting to astronomers is where it was found. It emerged from a data set focused specifically on nearby galaxy clusters, which means, in cosmic terms, Quipu is relatively close to us. Not close in any everyday sense, of course, but close, compared to many of the other enormous structures we've discussed tonight, several of which lie so far away that their light has been traveling toward us for well over 1 billion years. Finding a structure this massive, this close, was somewhat unexpected. It raises a quiet question. If something of this scale had gone unnoticed for so long, relatively nearby, what else might still be waiting, hidden in plain sight, simply because the right survey hadn't yet been pointed in the right direction? Like the South Pole Wall, and like the Great Walls we explored earlier, Quipu is not a single compact object. It's better described as a branching superstructure, a shape built from multiple connected clusters, rather than one continuous, solid mass. Picture something less like a single glowing sheet, and more like a great structure sprawling outward, in several directions at once. More specifically, astronomers describe Quipu as being made up of one main filament, with several smaller filaments branching outward from it. This gives Quipu a distinctly knot-like quality, not a simple line, or a flat curtain, like some of the walls we discussed earlier, but something more complex. Something with branches, and nodes, and connections stretching outward in multiple directions, almost like the roots of some enormous, ancient tree, spreading slowly through the dark. That branching structure is exactly where the name Quipu comes from. A quipu, in its original meaning, refers to an ancient recording system developed by the Inca, a method of communication and record-keeping using knotted cords. Instead of writing on paper, the Inca tied and arranged knots along different strands of cord, encoding information through the pattern, position, and connection of each individual knot. A single main cord might branch outward into many smaller cords, each one carrying its own particular meaning, all connected back to the same central strand. When astronomers looked at the shape of this newly discovered cosmic structure, one long, central filament, branching outward into smaller filaments, forming an intricate, knotted network across space, the resemblance felt almost too fitting to ignore. A structure built from galaxy clusters, connected by filaments of dark matter, branching outward in a way that closely echoed the ancient knotted cords used by the Inca centuries ago. And so, the name felt natural. Quipu, a cosmic structure, named after an ancient method of recording information through knots and branches, because its own shape, quite beautifully, mirrors that same pattern. There's something rather moving about that choice of name, if you sit with it for a moment. An ancient human tool, once used to record harvests, populations, histories, small knots, tied carefully along a cord, each one holding meaning. And now, that same word, borrowed to describe a structure of galaxy clusters and dark matter, branching outward across hundreds of millions of light years. Two systems, worlds apart in scale, connected quietly through a single shared shape. Now, let's talk about scale, because Quipu, despite its structural complexity, is genuinely enormous. Quipu lies relatively nearby, in cosmic terms, somewhere between approximately 425 million and 815 million light-years away, depending on which part of the structure is being measured. That range exists because Quipu isn't a single point in space. It's spread out, branching in different directions, meaning different regions of the structure sit at slightly different distances from us. In terms of overall length, Quipu has been described as spanning more than 400 megaparsecs, which translates to roughly 1.3 billion light-years, measured along its longest dimension. That places it firmly among the largest structures we've discussed so far tonight, standing shoulder to shoulder, in terms of raw scale, with structures like the Sloan Great Wall. And in terms of mass, the numbers become almost difficult to process. Quipu has been estimated to contain a mass of around 200 quadrillion times the mass of our Sun. 200 quadrillion solar masses. It's worth pausing, gently, On a number like that, not necessarily to fully grasp it, because numbers at this scale resist easy understanding, but simply to feel its weight for a moment. Our own sun already outweighs the Earth by hundreds of thousands of times. And Quipu's total mass is estimated at roughly 200 quadrillion suns, a figure so large it moves the conversation beyond planets, beyond stars, beyond individual galaxies entirely, into the realm of galaxy clusters, dark matter, and structures spanning well over 1 billion light-years. This combination, a length of over 1 billion light-years, paired with a mass measured in the hundreds of quadrillions of solar masses, places Quipu among the very largest, most massive structures ever described by astronomers. Not simply large in one dimension, the way some elongated filaments might be, but large across nearly every measure scientists use to describe cosmic scale. And yet, despite all of this, despite its staggering size, its immense mass, its branching, not like complexity stretching across more than 1 billion light-years, Quipu was only reported in 2025. Which means, quite remarkably, this entire structure, one of the largest ever described, has only recently entered our shared understanding of the universe. It's worth sitting quietly with that thought for a while. For most of human history, no one knew Quipu existed at all. Not because it wasn't there. It had been sitting quietly in the same relative region of space for hundreds of millions, if not billions, of years, patiently existing, entirely unnoticed, long before telescopes, long before galaxy surveys, long before anyone thought to look closely enough, in just the right direction, to notice its branching, knotted shape. And now, quite suddenly, in cosmic terms, we know it's there. A structure so massive that describing its scale requires units most people never encounter in ordinary life: megaparsecs, quadrillions of solar masses, hundreds of millions of light-years measured simply to describe its nearest edge. There's something deeply humbling about a discovery like this, especially when placed alongside everything we've explored tonight. We began this journey with modest galaxy groups, small, cozy gatherings of a few dozen galaxies, drifting quietly together through space. And now, we find ourselves resting beside Quipu, an enormous, branching structure, woven from galaxy clusters and dark matter, spanning well over 1 billion light-years, named after an ancient system of knotted cords because its shape so closely echoes something humans once used to record their own small, quiet histories. It's a strange, beautiful kind of symmetry, when you think about it. Long before we understood the true scale of the universe, we were already creating our own systems of knots, and threads, and branching connections, to hold on to meaning, and memory, and information. And now, looking outward, into the depths of space, we find the universe doing something remarkably similar, its own vast, branching threads of galaxies and dark matter, stretching quietly across the darkness, waiting patiently to be noticed. For now, let this settle gently. Quipu, vast, branching, and newly discovered, spreading outward across more than 1 billion light-years, woven from clusters, and filaments, and quiet threads of dark matter, hidden in plain sight until only very recently. Rest here for a while, if you'd like, drifting somewhere among its many branching arms, before we continue on, further outward still, into the segment yet to come. We touched briefly, a moment ago, on Quipu's staggering mass, but it's worth returning to that number once more, because it becomes even more meaningful once we understand the wider context surrounding its discovery. The researchers who first identified Quipu estimated its total mass at roughly 200 quadrillion solar masses. We sat with that number already, and it remains just as difficult to fully absorb the second time around. 200 quadrillion suns worth of material, bound together across more than 1 billion light-years, in a single branching structure of galaxy clusters and dark matter. But here's something we haven't mentioned yet. Quipu wasn't discovered in isolation. The very same study that identified Quipu also uncovered 4 additional superstructures, all located within that same broad region of nearby space. Which means Quipu, as extraordinary as it is, wasn't simply a lone anomaly, sitting quietly by itself in an otherwise ordinary stretch of universe. It was one of 5 major structures, found together, within a single, focused survey of our cosmic neighborhood. Let's take a slow, gentle walk through the others. Alongside Quipu, researchers identified a structure known as the Serpens Corona Borealis superstructure, named, like many cosmic formations, after the constellations in whose direction it happens to lie. Serpens, the serpent, and Corona Borealis, the northern crown, lending their names to a vast structure stretched somewhere far beyond the stars we associate with those constellations here on Earth. They also identified the Hercules supercluster, another enormous gathering of galaxy clusters, found within that same broad region of the survey, named after the constellation Hercules, much as its structural neighbors were named after the patterns of stars visible from our own small vantage point in space. And a third additional structure emerged as well, the Sculptor Pegasus superstructure, once again drawing its name from the constellations marking its general direction in the sky. So altogether, this single, focused survey revealed not just one enormous structure, but 5. Quipu, Serpens Corona Borealis, Hercules, Sculptor Pegasus, and one more, discovered alongside them in that same region of the nearby universe. 5 massive superstructures, uncovered together, within a single, relatively confined portion of the sky. It's a striking reminder that discoveries like Quipu rarely happen entirely on their own. Once astronomers develop the tools, and the surveys, capable of revealing one such enormous structure, they often find that its neighbors have been waiting there too, quietly unnoticed, simply because no one had yet mapped that region of space with enough depth and precision. Now, here's where the story becomes even more remarkable, because it isn't just about how many structures were found. It's about how much of the surrounding universe those 5 structures actually contain. According to the discovery paper, these 5 superstructures, together, hold approximately 45% of all galaxy clusters found within the observed region. Let that settle for a moment. 5 structures, not the entire volume of space being studied, but 5 specific, connected formations within it, account for nearly half of every galaxy cluster identified across that entire survey. And yet, remarkably, those same 5 structures occupy only a small fraction of the total volume of space being studied. Vast in terms of mass, and dense in terms of galaxy clusters, but comparatively modest, in terms of the sheer amount of space they actually take up. Nearly half of the region's clusters, concentrated into a surprisingly small portion of its overall volume. It paints a picture that echoes something we touched on earlier in this journey, the idea of a cosmic web, made of dense, concentrated regions, separated by vast stretches of comparative emptiness. Here, in this particular survey, that pattern becomes especially clear. Galaxy clusters aren't spread out evenly across the surveyed volume. They gather, densely, within these 5 enormous structures, leaving the rest of the surrounding space far more sparsely populated by comparison. The same pattern holds true, too, when researchers looked beyond just galaxy clusters, and considered galaxies more broadly. Together, these 5 superstructures contain approximately 30% of all galaxies found within the surveyed region. Not just clusters of galaxies, but individual galaxies themselves, nearly a third of everything counted across the entire study, concentrated within these 5 connected formations. 30%, again, held within only a small portion of the overall volume being surveyed. It reinforces that same underlying idea. These structures aren't simply large. They're disproportionately significant, holding far more material, relative to their size, than the surrounding regions of space around them. And the pattern continues even further, once researchers examine not just galaxies and clusters, but matter itself, including the vast quantities of unseen dark matter that make up so much of the universe's overall mass. According to the study, these 5 superstructures together contain roughly 25% of all matter found within the surveyed region. A quarter of the total matter, concentrated within these 5 formations alone. And yet, remarkably, all of that, nearly half the region's galaxy clusters, close to a third of its galaxies, and a full quarter of its matter, is packed into structures occupying only about 13% of the surveyed volume. 13% of the space, holding 25% of the matter. It's worth sitting with that imbalance for a quiet moment. If matter were spread evenly throughout the universe, filling space uniformly in every direction, you'd expect these proportions to roughly match. 13% of the volume containing somewhere close to 13% of the matter. But that isn't what these numbers reveal at all. Instead, we find a universe that gathers, that concentrates, that pulls enormous quantities of galaxies, clusters, and matter into relatively confined, densely packed formations, while leaving vast stretches of space around them comparatively empty, sparse, and quiet. It's the same underlying story we've been following throughout this entire journey, expressed now through hard numbers, drawn from careful, patient measurement. The universe doesn't spread its material out evenly. It weaves it, instead, into dense, connected structures, into walls, and filaments, and branching, not like superstructures like Quipu, leaving the space between them stretched thin, and quiet, and largely undisturbed. 5 structures, discovered together, within a single region of the nearby universe, holding, between them, nearly half of that region's galaxy clusters, close to a third of its galaxies, and a full quarter of its total matter, all folded into just 13% of the available space. It's a quiet, humbling kind of statistic to rest with. because it suggests that even within our own relatively nearby corner of the universe, so much of what exists is concentrated into just a handful of enormous, branching formations. Quipu, Serpens Corona Borealis, Hercules, Sculptor Pegasus, and their unnamed companion, while everything else, all the space stretching quietly between them, remains comparatively sparse by comparison. We are, after all, part of this same broader picture. Our own galaxy, and our own local group, sit somewhere within this same vast, uneven arrangement of matter, perhaps drawn, ever so slightly, toward one of these dense, distant concentrations, in much the same way the South Pole wall may be gently tugging at us from a different direction entirely. For now, let this settle quietly. 5 vast superstructures, discovered together, in a single careful survey of the nearby universe. Nearly half of the region's clusters. Close to a third of its galaxies. A full quarter of its matter. All of it, gathered into just a small fraction of the available space, while the rest of that vast region rests quietly around them, sparse, and dark, and comparatively still. Rest here for a while, if you'd like, letting these proportions settle gently in the mind, before we continue drifting onward, further into the segment still to come. We left off resting in that quiet imbalance, nearly a quarter of all matter, gathered into just a small fraction of available space. And it's worth confirming that number once more, because it applies not only to the region immediately surrounding these 5 great superstructures, but to the broader portion of the observable universe covered by this particular survey. Roughly 25% of the matter within that surveyed volume, held within structures occupying only about 13% of the space itself. It's the same striking imbalance we sat with a moment ago, but here, extended outward, across an even larger portion of the observable universe. A quiet, consistent pattern, appearing again and again, the deeper astronomers look. Now, here's where this story moves from simple observation into something with real, practical consequences for how we measure the universe itself. The team who discovered Quipu made a rather striking claim. These 5 superstructures, they suggested, are so massive, so concentrated, that they can actually influence our measurements of the universe's local expansion rate. To understand why that matters, it helps to remember that astronomers use the motion of distant galaxies to help calculate how quickly the universe is expanding. But galaxies don't move in perfectly smooth, predictable patterns. Their motion is influenced by the gravity of everything around them, including enormous, nearby concentrations of mass, like Quipu and its 4 companions. If a significant portion of nearby space contains structures this massive, pulling on surrounding galaxies with extra gravitational force, it can subtly distort our local measurements, making the expansion rate appear slightly different in our immediate cosmic neighborhood than it might elsewhere in the universe. It's a delicate, almost humbling idea. Some of the smallest uncertainties in modern cosmology, tiny inconsistencies that scientists have puzzled over for years, may be partly explained by enormous structures like these, quietly distorting our local view of an otherwise uniform, expanding universe. And the influence of these giant structures doesn't stop there. Structures on this scale can also affect something called gravitational lensing, the subtle bending of light as it passes near an enormous concentration of mass. We often think of gravitational lensing in terms of a single massive galaxy, or perhaps a dense cluster, gently curving the path of light from something far behind it. But a structure as vast as Quipu, spanning well over 1 billion light-years, can produce that same lensing effect on a much larger scale, subtly bending and distorting the light of countless distant objects, simply by being positioned somewhere along its path. This means that if astronomers aren't accounting for structures like Quipu, some of their most distant observations of galaxies, or quasars, or other faint background objects, could be subtly skewed, their true positions, or shapes, slightly altered by the gravitational influence of an enormous, foreground structure they hadn't yet identified. Even something as fundamental as the cosmic microwave background, the faint afterglow of the Big Bang itself, spread across the entire sky, can be gently influenced by matter concentrations on this scale. As that ancient light travels toward us, across billions of years, it passes through countless regions of space, some denser, some emptier than others. Structures as massive as Quipu can leave a faint, subtle imprint on that light along the way, a small distortion, layered quietly into some of the oldest light in the entire universe. This is part of why structures like these matter so deeply to what scientists call precision cosmology, the careful, exacting science of measuring the universe as accurately as possible. Every unaccounted for structure, every hidden concentration of mass, introduces a small uncertainty into calculations that scientists are trying to make as precise as humanly possible. Finding structures like Quipu doesn't just expand our sense of cosmic scale. It actually helps refine our measurements of the universe as a whole. And yet, despite all of this influence, despite their staggering size, and their surprising effect on some of our most careful cosmological measurements, the researchers behind this discovery offered a rather humbling perspective on structures like Quipu. They don't consider them permanent. According to the discovery team, these enormous superstructures should be understood as temporary arrangements, rather than fixed, lasting cosmic objects. Structures like Quipu are not held together the way a single galaxy, or even a tightly bound cluster, might be. Their component parts, the individual clusters and filaments woven throughout, aren't gravitationally locked together as one single, permanent system. Which means, as strange as it may sound, a structure spanning well over 1 billion light-years, containing 200 quadrillion solar masses, is not expected to last forever in its current form. The paper argues that, given enough time, structures like these will eventually break apart. As the universe continues expanding, superstructures like Quipu are expected to gradually fragment into smaller, individually collapsing units, clusters and groups drifting apart from one another, no longer held together as one grand, unified formation. It's a strange thing to consider. A structure so vast it can bend light, and shift our measurements of cosmic expansion, and yet, on a long enough timescale, destined to slowly dissolve. Not through any dramatic collapse, or violent event. Simply through the same slow, patient stretching that has been shaping the universe since its very beginning. Over time, the threads connecting Quipu's many branches will loosen. Its clusters will drift further apart. And eventually, what we now call a single, unified superstructure may exist only as a scattered collection of smaller, more modest formations, the echo of something once far larger, quietly fading into the broader expansion of space. There's something almost poetic in that. Even the largest structures we've explored tonight, walls stretching over 1 billion light-years, branching superstructures woven from clusters and dark matter, are not truly permanent. They're temporary arrangements, shaped by gravity for a time, before the universe's own expansion gradually pulls them apart again. Now, let's shift our attention briefly to another way astronomers have searched for enormous cosmic structures, not through galaxies alone, but through some of the brightest, most energetic objects in the known universe. Large quasar groups, often shortened simply to LQGs, are enormous associations of quasars, incredibly bright, distant objects, powered by supermassive black holes actively pulling and surrounding material. Because quasars are so extraordinarily luminous, they can be observed across enormous distances, even near the very edge of the observable universe. Some large quasar groups have been found to span billions of light-years, structures so vast that their discovery genuinely challenged existing expectations about how large a single cosmic structure could possibly be. For years, some of these enormous quasar groupings pushed right up against, and in some cases beyond, the theoretical limits many cosmologists had assumed the universe's largest structures should respect. It's a reminder that galaxies and galaxy clusters aren't the only way astronomers can map the largest patterns in the universe. Sometimes, the brightest, most energetic objects available offer their own unique way of tracing structure across unimaginable distances. And quasars aren't the only unconventional tracers astronomers have turned to in recent years. Some newer studies have begun using gamma-ray bursts, brief, extraordinarily powerful flashes of energy, among the most luminous events known to occur anywhere in the universe, as tools for mapping large-scale structure as well. Because these bursts are so incredibly bright, they can be detected from extreme distances, even from galaxies too faint, or too far away, to study easily through other means. By carefully tracking where these gamma-ray bursts occur across the sky, researchers have found that they, too, can help reveal hidden patterns in the distribution of matter, faint echoes of the same underlying cosmic web we've been exploring throughout this entire journey. It's a beautiful example of how many different paths can lead toward the same underlying truth. Galaxy surveys, redshift measurements, quasar groupings, even brief, blinding flashes of gamma-ray light, gone in a matter of seconds. Each one, in its own way, offering a slightly different lens through which to view the same vast, underlying structure, the same great cosmic web, stretched quietly across the universe, patiently waiting to be traced, one method, one observation, one flash of distant light at a time. For now, let all of this settle gently. Structures so massive they bend starlight, and subtly shift our measurements of cosmic expansion, and yet, ultimately, temporary, destined to slowly drift apart across the coming eons. Quasars, blazing brightly enough to outline structure across billions of light-years. And gamma-ray bursts, brief and blinding, offering brief glimpses into patterns that might otherwise remain hidden entirely. Rest here for a while, if you'd like, letting these different threads settle quietly together, before we continue on, drifting further outward, into the segment still to come. Let's continue with gamma-ray bursts a little longer, because this method of mapping the universe has led to some of the strangest, most debated structures we'll encounter in this entire journey. We touched briefly, a moment ago, on the idea that gamma-ray bursts can help reveal hidden patterns in the distribution of matter. But it's worth slowing down here, because some of what astronomers have found using this method doesn't simply confirm the structures we already knew about. It suggests something new entirely, structures so large, so unusual, that they've sparked genuine debate within the scientific community about whether our basic assumptions about the universe still hold. Rather than only counting galaxies and mapping their positions through redshift surveys, some researchers have taken a different approach. They've looked instead for unusual clustering within gamma-ray burst data itself, searching for places in the sky where these brief, brilliant flashes of energy seem to gather more densely than random chance alone would predict. And what they've found, in some cases, is almost difficult to describe using the same vocabulary we've used throughout tonight. Some of these gamma-ray burst features are so enormous that their size is measured not in hundreds, but in thousands of megaparsecs. If you recall, a single megaparsec already stretches across more than 3 million light-years. A structure measured in the thousands of megaparsecs pushes the very idea of cosmic structure into territory few astronomers expected to encounter at all. These features rank among the largest structures ever reported, full stop, larger, in some cases, than even the Great Walls and branching superstructures we've spent so much of tonight exploring. One particularly strange example is something researchers named the giant GRB ring. Unlike the walls, filaments, and branching superstructures we've discussed so far, this feature doesn't take the shape of a line, or a sheet, or even a knotted, branching network. Instead, it was reported as something closer to a ring, a roughly circular concentration of gamma-ray bursts, clustered together in a shape that, quite genuinely, resembles a great, glowing loop stretched across an almost unimaginable portion of the sky. Try, for a moment, to picture that. Not a wall, stretched long and flat across space. Not a branching structure, spreading outward like the roots of some ancient tree. A ring. A vast, curving loop, traced out not by galaxies directly, but by the brief, blinding flashes of some of the most energetic explosions known to occur anywhere in the universe. It's a genuinely strange shape to encounter, this far into our journey. And its strangeness is part of why it's drawn so much scientific attention. Alongside the giant GRB ring, researchers have identified another unusual feature, sometimes called the giant arc. A long, curving structure, traced through the distribution of matter across an enormous portion of the sky. Together, structures like the giant arc and the big ring have led some researchers to raise a rather profound question. Do features this size challenge one of the most fundamental assumptions in modern cosmology, the idea that, on the very largest scales, the universe should appear roughly uniform in every direction? This idea, often called the cosmological principle, suggests that if you looked at a large enough region of the universe, in any direction, it should look statistically similar. No enormous, unusual concentrations. No structures so large they break the expected pattern. Just a smooth, roughly even distribution of matter, once you zoom out far enough. but structures like the giant arc and the giant GRB ring are so extraordinarily large that some researchers wonder whether they might sit right at the edge of what this principle should even allow. If real, structures at this scale would represent some of the most significant unsolved puzzles in modern cosmology, hints, perhaps, that our current models of the universe's largest scale behavior may need further refinement. It's important to say, gently, that these particular structures remain genuinely debated within the scientific community. Unlike some of the walls and superstructures we explored earlier, tonight, features like the giant arc and the giant GRB ring are still being carefully studied, questioned, and in some cases, challenged by other researchers, who wonder whether these apparent patterns might arise from statistical quirks in the data, rather than genuine physical structures. Science, especially at scales this enormous, moves carefully and slowly, weighing new evidence against old assumptions before settling on any firm conclusion. But even amid that uncertainty, these structures remind us of something important. Our picture of the universe's largest scale architecture is still being actively written. Even now, in the present, this story continues to unfold, its final chapters, if such a thing even exists, still very much unwritten. And that uncertainty brings us, finally, to what may be the single largest structure we'll encounter throughout this entire journey, the Hercules Corona Borealis Great Wall. This structure has been reported, by some researchers, as possibly the largest ever identified, with an estimated extent approaching 10 billion light-years. It's worth pausing, quietly, on that number, because it dwarfs almost everything else we've discussed tonight. The Sloan Great Wall, at just over 1 billion light-years, once seemed almost impossibly large. Quipu, spanning slightly more than 1 billion light-years, felt staggering in its own right. And here, we find a structure reportedly extending nearly 10 times that distance. 10 billion light-years. It's worth being honest, here, in the same careful, measured way scientists themselves have approached this structure. Its reality, and its precise interpretation, remain genuinely debated. Some researchers question whether what's being observed truly represents one single, connected structure, or whether it might instead be a chance alignment of separate, unrelated features, spread across the same general direction of sky. This uncertainty doesn't make the structure any less fascinating to consider. But it does mean we should hold this particular number a little more loosely than some of the others we've explored tonight. The Hercules Corona Borealis Great Wall was first proposed back in 2013, inferred not from galaxy surveys directly, but once again from the sky distribution of gamma-ray bursts, much like several of the unusual structures we just discussed a moment ago. Researchers noticed an unusual concentration of these brief, brilliant flashes, clustered together across a broad region of sky, hinting at the presence of some enormous, underlying structure stretching far beyond what conventional galaxy surveys had mapped up until that point. Structurally, this formation is usually described as a filament, rather than a wall, despite what its name might suggest. Which means it's generally understood as a long, connected string of galaxy groups and clusters, rather than a flat, compact structure, or a simple, blob-like shape. And in fact, the name itself carries a small irony, once you look closely. Despite being called a wall, researchers now believe the Hercules corona Borealis Great Wall is actually more roundish in overall shape, rather than flat and sheet-like, the way many of the other great walls we discussed earlier tonight tend to be. Names, in astronomy, are often assigned early, based on initial impressions, and sometimes those names persist, even after later research reveals a slightly different underlying shape. It's a small reminder that even in careful, rigorous science, first impressions don't always perfectly capture the full truth of what's later discovered. The structure's reach extends further than its name alone might suggest, too. While it's named after the constellations Hercules and Corona Borealis, the structure isn't confined to that region of sky alone. It also extends into the directions of Lyra, Boötes, and Draco, stretching across a remarkably broad portion of the observable sky, rather than remaining neatly confined within just the two constellations mentioned in its name. It's worth remembering, here, that constellations themselves are simply patterns we've drawn onto the sky, based on how stars happen to appear from Earth's particular vantage point. They have nothing to do with actual distance, or true physical structure. When astronomers say a structure extends into Lyra, Boötes, and Draco, they mean its true physical shape happens to stretch across that same broad region of Earth's sky, even though the structure itself lies unimaginably farther away than any of the individual stars that make up those familiar constellation patterns. And finally, let's return to that almost incomprehensible number one more time, if only to sit with it a little longer. If the Hercules corona Borealis Great Wall truly spans the distance researchers have proposed, light would need approximately 10 billion years to travel from one end of the structure to the other. 10 billion years. For context, our own universe is generally understood to be somewhere around 13.8 billion years old. Which means, if this structure is real, and if its proposed scale holds up under continued scrutiny, light crossing from one edge to the other would need a span of time representing nearly 3/4 of the entire history of the universe itself. It's difficult to hold a number like that gently. Every other structure we've explored tonight, as vast as each one felt in its own moment, existed comfortably within a universe old enough, and large enough, to easily contain it. But a structure spanning 10 billion light-years pushes right up against the very outer edges of what feels comprehensible, a scale so enormous that some researchers wonder whether structure, in the traditional sense, is even the right word to use at all. And perhaps that uncertainty is fitting, in its own way, as we near the far edge of tonight's journey. We began this exploration with something small and familiar. A galaxy group. A modest gathering of a few dozen galaxies, drifting together through space, cozy and close-knit by cosmic standards. And now, hours later, we find ourselves resting beside a structure so large, so uncertain, so close to the very boundary of what current science can confidently describe, that its own existence remains an open question. Perhaps that's exactly where a journey like this should lead. Not toward a tidy, final answer, but toward a quiet, honest acknowledgement of just how much remains unknown, how much of the universe's largest architecture is still being carefully mapped, questioned, debated, and slowly, patiently understood, one gamma-ray burst, one galaxy survey, one careful measurement at a time. For now, let all of this settle quietly. Rings of gamma-ray bursts, curving through the sky in shapes no one fully expected. Arcs stretching far enough to test our most basic assumptions about the universe's own uniformity. And somewhere beyond all of it, a structure so vast, so debated, that light itself would need 10 billion years just to cross from one end to the other, nearly the entire lifetime of the universe itself, condensed into the length of a single, uncertain, magnificent structure. Rest here for a while, if you'd like. There's no need to resolve any of this tonight. Simply let these final, uncertain shapes drift quietly through the mind, rings, and arcs, and walls that might not truly be walls at all, echoes of a universe still being mapped, still being understood, still patiently waiting, in the vast, quiet dark, to be fully known. We left off resting beside a structure so vast that light itself would need 10 billion years to cross it. And it's worth returning there gently, for just a moment longer, because that particular structure carries with it an important lesson about how careful, patient, and cautious real science actually is. Despite its staggering proposed size, the Hercules Corona Borealis Great Wall is still treated with real caution by the scientific community. It has not been confirmed as a single, connected physical structure, in the same way some of the smaller walls and superstructures we explored earlier tonight have been. Some researchers remain genuinely uncertain whether what's being observed represents one true, unified formation, or whether it might instead be several separate, unrelated features, simply appearing to align when viewed from our particular vantage point in space. This kind of caution isn't a weakness in the science. It's actually one of its greatest strengths. Rather than rushing to declare something the largest structure ever found, and leaving it there, researchers continue testing, questioning, and re-examining the evidence, refining their understanding a little further with each new study. And this caution extends well beyond just the Hercules Corona Borealis Great Wall alone. Many of the largest structures we've discussed throughout this journey share a similar complication. Some of them may not be fully gravitationally bound, meaning their various parts, clusters, filaments, and groups, aren't necessarily locked together by gravity into one single, permanent system. We touched on this earlier, when discussing superclusters, and again when exploring Quipu. And it's part of why astronomers sometimes debate whether structures like these should really be counted as single objects at all, in the same way we might casually think of a galaxy, or a solar system, as one clearly defined object. If the different parts of a structure aren't gravitationally holding each other together, is it truly one single formation, or is it simply a temporary pattern, an arrangement that happens to look connected right now, but won't necessarily remain that way? It's a subtle, important distinction. And it leads directly into something we touched on earlier as well, when discussing Quipu specifically. Many astronomers believe that some of the largest named structures in the universe may ultimately be temporary patterns within the broader flow of cosmic matter, rather than permanent, lasting objects in their own right. Structures that exist for now, shaped by the current arrangement of gravity and matter, but which may gradually dissolve, stretch apart, or reorganize entirely, as the universe continues its slow, patient expansion across the eons still to come. There's something quietly beautiful in that idea, if you sit with it gently. Even the most enormous structures we've explored tonight, walls stretching over 1 billion light-years, branching superstructures woven from galaxy clusters and dark matter, may not be permanent fixtures of the universe at all. They may simply be passing arrangements. Vast, magnificent, and genuinely real in this particular moment of cosmic history, and yet, ultimately, temporary, the way clouds drifting slowly across an evening sky are real and beautiful, and yet never quite permanent either. Now, this growing awareness of ever larger structures, walls, filaments, rings, and arcs, some approaching, or even exceeding, 1 billion light-years in length, has led to real, ongoing debate within cosmology, surrounding something called the cosmological principle. We touched on this briefly a little earlier, but it's worth exploring a bit further now, as we near the end of this particular journey. The cosmological principle suggests that, on a large enough scale, the universe should appear roughly the same everywhere, smooth, evenly distributed, without any single region containing an unusually large, unusually dominant structure. It's one of the foundational assumptions underlying much of modern cosmology, shaping the way scientists build models and interpret observations of the universe as a whole. But every time researchers uncover a structure larger than the last, a wall exceeding 1 billion light-years, a branching superstructure like Quipu, or stranger formations like the giant arc and the giant GRB ring, that assumption gets tested a little further. Even so, it's worth being clear and gentle here. Most cosmologists don't treat these enormous claimed structures as definitive proof that our basic models of the universe are wrong. Instead, they approach them with careful curiosity, studying them closely, testing them against independent surveys, and waiting for further confirmation before drawing any firm conclusions about what these massive formations truly mean for our broader understanding of cosmic structure. Science, especially at this scale, tends to move slowly and carefully, by design. Part of what makes this conversation so nuanced is something called the transition to cosmic homogeneity, a concept describing the scale at which the universe is expected to finally smooth out and appear roughly uniform once you're looking across a large enough volume of space. On smaller scales, we've spent this entire journey exploring just how clumpy and textured and unevenly distributed matter truly is. Groups, clusters, superclusters, walls, and filaments, and branching structures like Quipu. But cosmological theory suggests that if you zoom out far enough, averaging across a sufficiently enormous volume of space, all of that clumpiness should eventually smooth out into something far more uniform. And that's precisely why structures like the ones we've explored tonight matter so much to ongoing research. Superclusters and great walls demonstrate, quite clearly, that the universe remains genuinely clumpy, genuinely textured, even on scales far larger than most people would ever casually assume. The question researchers continue exploring is simply this: at what scale does that clumpiness finally give way to smoothness? And do some of these newly discovered, ultra-large structures push right up against, or even beyond, where that transition was originally expected to occur? It's also worth pausing to acknowledge something important about how all of these measurements actually work in practice. Every size, every distance, every structure we've discussed tonight refers specifically to what astronomers can currently observe, which depends heavily on the depth and quality of the particular survey used to detect it. Different surveys reach different distances. Different instruments have different sensitivities. And astronomers themselves must make careful decisions about how to define a structure in the first place, when analyzing the raw distribution of galaxies, or quasars, or gamma-ray bursts, scattered across their data. This means the exact boundaries of these enormous formations aren't always fixed, permanent facts, discovered once and settled forever. They're often best understood as evolving interpretations, refined, revised, and sometimes reconsidered entirely, as our tools and our techniques continue to improve over time. And even after considering every wall, every filament, every branching superstructure we've explored throughout this entire journey, it's worth remembering something quietly humbling. The observable universe itself is larger still than any single structure within it. Every wall, every filament, every enormous, branching supercluster, all of it represents only a part of the whole, fragments of a much larger tapestry, stretching outward in every direction, far beyond even the largest individual formation we've discussed tonight. Even a structure spanning 10 billion light-years, should its full scale eventually be confirmed, would still represent only a portion of the entire observable universe, a universe whose true edges extend even further outward still, into regions barely glimpsed, let alone fully mapped. Many of the largest confirmed, and reasonably well-supported structures we've explored tonight tend to stretch somewhere around 400 megaparsecs or more, roughly 1.3 billion light-years in length. That figure keeps reappearing throughout tonight's journey, again and again, almost like a quiet, recurring landmark, the Sloan Great Wall, Quipu, and several other structures we've touched on, all resting somewhere near that same extraordinary scale. But even that impressive, oft-repeated number isn't necessarily a final, permanent limit. New findings continue pushing the boundaries of what's considered possible, further outward, again and again. Each time a new survey reaches a little deeper into space, or maps a broader region with greater precision, there's a real possibility that some new structure will be uncovered, one that quietly exceeds everything discovered before it. This is precisely why the label largest known structure tends to shift and change every so often as astronomy continues to advance. Which brings us, finally, to a rather gentle, fitting way to close this particular part of our journey. The structures we've explored together tonight, from the earliest, small galaxy groups we began with, all the way to sprawling formations stretching across 10 billion light-years, represent our current understanding. Careful, patient, evidence-based understanding, built through decades of surveys and measurements and quiet scientific persistence. But it remains, and will likely always remain, a work in progress. Today's record holder, whichever structure currently carries that title, may quietly give way tomorrow to some newly mapped superstructure, waiting patiently somewhere in a region of sky not yet fully surveyed. Just as Quipu itself was only recently uncovered, hiding in relatively nearby space for who knows how many billions of years, simply waiting for the right survey, pointed in the right direction, to finally reveal its branching, knotted shape. There's something deeply peaceful and resting inside that uncertainty, rather than resisting it. The universe, it turns out, is far larger, far stranger, and far more intricately structured than the human mind was ever really built to casually imagine. Groups drifting quietly within superclusters. Superclusters, in turn, forming part of vast branching filaments. Filaments weaving together into walls, and rings, and arcs, some of them so large that their very reality remains gently, respectfully debated. And beyond all of it, still, an observable universe larger than anything we've discussed tonight, patient, vast, and quietly waiting for its next layer of structure to finally be revealed. For now, let all of this settle, slowly, and gently. There's no need to hold on to every name, every distance, every careful scientific caveat we've explored throughout this long journey together. Simply let the shapes remain, groups, and clusters, and superclusters, and walls, and branching, not like formations, stretching outward, further and further, into the dark. Somewhere, quietly nested within all of it, our own small galaxy continues drifting gently through space, connected, in some small way, to almost everything we've discussed tonight, to Quipu's branching arms, to the distant curve of the South Pole Wall, to ancient filaments of gas once forged inside the hearts of long-vanished stars. We are, in the end, part of the very structure we've spent all this time exploring. Rest now, in that quiet knowledge, if you'd like. Let your thoughts drift gently outward, one final time, beyond galaxies, beyond clusters, beyond even the largest walls and superstructures we've traced together tonight, into the vast, patient, endlessly unfolding architecture of the universe itself. And let yourself rest there, quietly, for as long as you need.